Hi, welcome back to Quantum Computation Simplified. I'm Kadresan. In this video, let's see how quantum computing can be applied for financial research or analysis. Question comes, why should we do? It's because there are a lot of challenges with classical computing in finance. I listed some of them, but there may be many more. The first and foremost is the scalability issue. Classical computers process data sequentially, making it challenging to handle massive data sets or high dimensional problems efficiently. So, when a banker wants to look at the borrower's data, there'll be a huge number of data. And higher dimensional, what I mean is, what are the different attributes associated with each borrower? Or in a stock case, there are multiple parameters which determines the return, right? So which that's what I try to say, high dimensional problems. Okay, complex optimization problems, tasks like portfolio optimization and risk assessment involve complex calculations that can be computationally intensive for classical systems. Simulation limitations. Okay, so when you want to do like Monte Carlo simulation, it's better to have large samples. So accurately simulating financial markets and instruments often require computational resources beyond the capabilities of classical computers. May not be the case for all every time. It may be, or why should we say it's beyond the capabilities? Maybe because within the time frame available to us, I need to take a quick decision like where do I invest immediately? Okay. So it becomes very difficult with classical computers. So how quantum computing is going to help. We know that the computation methodologies, there's a paradigm shift, right? To overcome these limitations, we are going to leverage the principles like superposition and entanglement. Okay, I hope you are familiar with quantum computing. If you are not, I request you to go through my introductory lectures on quantum computing. Okay, so these principles enable the process of complex computations more efficiently. Okay, so this statement you don't have to accept now. Later, when we see examples, you will appreciate that. In addition, large financial institutes they got into quantum research. Companies like JP Morgan, HSBC, Citigroup, Wells Fargo. I listed only a few of them. There are many more banking guys are into quantum research. For what? To improve portfolio optimization, derivative pricing, risk analysis, and secure financial transactions. There may be some more applications in addition to what I have listed here: portfolio valuation, fraud detection, optimization of my investment. Of course, on the cyber security, I have a different video already, right, on quantum cryptography. Okay, so this is just to give an idea why should we look quantum computing for finance. So let's see how it helps. Okay, quantum computers utilize superposition to represent vast landscape of borrower possibilities at once. Can handle very many number of borrowers with ease. Classically, exploring each scenario individually becomes exponentially prohibitive for realistic financial risk analysis. It's not only for risk analysis, even for portfolio optimization. So let's take an example. Okay, I want to do analysis on fraud detection. Okay, I have two borrowers and I want to know what's the probability of one guy becoming a defaulter. So I need to consider various options, right, or various combinations. What are they? That both the guys are good, first guy is bad, first guy alone is bad, second guy alone is bad, or both are bad. Okay, so even with the two borrowers, we have 2 to the power of 4, sorry, 2 to the power of 2 combinations. Assume that we have 100 borrowers, we have 2 to the power of 100 combinations of defaulters are possible, right? And definitely a large bank will have thousands of borrowers. Of course, and this logic is not only for fraud detection, even for trading strategies. We have thousands of stocks available. So which one I should choose, which two I should choose, which three I should choose, or I want to invest on everything. What is my probability of getting my return? So like that, the problem is becoming complex, right? In classical computing, portfolio management. Where do I invest? Risk assessment. I hope you got some idea about the explosion of the problem in an exponential way, and quantum computing is going to handle it so easily. It processes these configurations in parallel due to the superposition principle, significantly reducing computation time for large portfolios. Okay, so definitely for two borrowers, we will not use quantum computing. When the number of borrowers are more, very a large number, definitely quantum computing is going to be useful. Generally, we encode the probabilities of default as amplitudes of quantum states. You know amplitudes, right? Quantum gates like rotation gates are used to adjust these amplitudes based on borrowers' individual default probabilities. Okay, later you will understand once you work on an example. Quantum computing avoids the need for exhaustive calculations of probabilities across scenarios, which is required in classical computations. So you want to work different scenarios. In classical way, you have to repeat, whereas here you can do it with one problem. I'm sorry, configuration alone. This also you will appreciate once you see the example. So overall, I would say that the complexity from exponential, it reduces to polynomial. I'm sorry. All right. Now let us understand the next step. There is something called quantum amplitude estimation. It's a quantum algorithm. Generally, it's used as a subroutine for the applications what we are interested, like what we saw in the earlier case, portfolio optimization, risk analysis, and all, right? So what exactly it does? It estimates the probability or amplitude. You know that probability and amplitude are related, right? Probability is nothing but the square of absolute value of amplitude. So this helps us to estimate the probability of a desired outcome in a quantum state. It provides a quadratic speedup over classical Monte Carlo methods. So that's the first advantage. You get speed up. I mean, you are able to speed up the computation. In addition, it has got other advantages also. Reusability of measurements. Okay, so you build up one problem, then from the outcome, once you make we know that at the end of quantum computing, you have to make a measurement, right? Afterwards, from the measured value, you can do some analysis and get different type of analysis you can do. Okay, from the same data coming out using, of course, classical computing. Higher precision for tail probabilities. Okay, so this is another important application. I have not seen it, but what does it mean is, suppose you take a case of borrower. Okay, there may be one borrower who whose probability of becoming a defaulter may be less, but if he becomes, then it will have a huge impact. Possibly he would have borrowed a large amount of money. Scalability with state preparation. That's what we have seen in the previous slide. It goes exponential, right? 2 to the power of n. Handling correlated systems. So this is another very important advantage. We know that there's a principle or phenomenon called entanglement, right? So that helps us to correlate the data. for example, okay, I have 100 borrowers. Maybe in that, 5 borrowers from same company, which may not be doing well. So there's a likelihood that all 5 can go bad. Okay, all 5 can go as a defaulter. So like that, we can correlate, or a son, father and a son, or 2 brothers. So such things we can do it easily in quantum computing, which is little complex in classical computing. Again, so as I told you, this is like a heart of a finance problems. There are many algorithms, many different algorithms of QAE. So the standard one, okay, so I try to compare with the 3 factors, the NIS compatibility. Basically, when I say NIS compatible, when you use less number of qubits, it becomes more compatible. Similarly, when it is less prone to noise, or less, the noise impacts less, then it is better compatibility. Circuit depth, right? So the number of steps involved in the calculation. Classical overhead means post processing the data. Okay, so standard QAE. So typically, if you take this approach, you need, even for one borrower, you need 4 qubits. Whereas iterative QAE, which is what we are going to use it in our example, even for 3 borrowers, we need only 3 qubits. Okay, so the compatibility wise, it is good. And in fact, the answer also, this gives better than that. So with the minimum number of qubits, as far as circuit depth is concerned, it's moderate, but really you don't have to worry, because in general, we are not going to build the circuit. We can make use of already available uh, algorithms, right? So we'll not even know how many gates are being used unless you want to develop your own QAE algorithm. Okay. All right. So this just a list of 4. There are many more, and as I told you, you can come out with your own algorithms also. And if you want to know more about them, in fact, this website, it's a Quizkit community website. They run a sample problem with one borrower, different algorithms, and try to explain to us how the result looks like. Okay. So let's try to understand a little more about quantum amplitude estimation. What exactly it does? So it basically, when you want to use when we develop an quantum amplitude estimation algorithm, we need to do we need to build 2 circuits, or 2 operators, A and Q. What is A? A actually encodes the problem, right? The problem may be with respect to borrowers, or with respect to choosing the portfolio, stock, whatever may be. So we are trying to put the problem, right? The Q, it's called Grover operator. It exactly uses Grover algorithm. I hope you know. If you don't know, please see my earlier videos on Grover algorithm. And we know that Grover algorithm repeatedly amplifies the amplitudes of the desired state. What state we are interested in, that is what it is going to amplify that. So here also we are going to do similar way. So this equation, whatever you see the computations here or the mathematics here, it is again just for one borrower, or one stock. Okay, we start with the 0 state always, correct? And where when this operator A operates on ket 0, you will get some ket 0 and ket 1. And we are interested in this state, ket 1 state, which is what we call it as is good state. Actually, it is a bad thing for borrowing, but for lending, but typically they call us this as the good state. Okay, so we are interested to encode this information by using operator A. So what is operator Q? So it has got again 4 sub operators, we can say. A is the same as what is given here. S0, A dagger, which is complex conjugate of A, then S psi 1. Okay, and S0 and S psi 1 are reflections about state 0 and the state which we are interested in. Okay, so that is what we have to do as per Grover algorithm, right? So now let's arrive at what is A, because every operator should have a unitary matrix. So in this case, we are trying to build the operator with RY gate, okay, rotation with respect to y axis. So that can be expressed like this: cos theta by 2 minus sin theta by 2, sin theta by 2, cos theta by 2. And A dagger is nothing but complex conjugate of it. So wherein we'll interchange this. So we have A and A dagger. Now, how do we get S0? S0 as by Grover's algorithm definition, it is nothing but identity matrix minus 2 into get 0 bra 0. So we can arrive at this matrix. S psi 1. So this should be the state psi, but in this case, since we are working on only one uh, operator, sorry, one borrower, we are just putting one. Okay, so that will result in this matrix. So how do we calculate Q? We have to do matrix multiplications in this order. So when you do that, you will end up the matrix elements like this. And if I take minus out, I'll get the matrix like this. And now you can see these two are almost the same, right? Cos minus sine, sine cos, except that instead of theta by 2 here writes theta. That means this is nothing but, of course, there is a minus sign, minus rotation around y-axis, but twice the angle. Okay, and this minus you can neglect it because it is a global phase which will not impact any of our computation. Okay, so Q is nothing but Ry 2 theta. Okay, why did I consider Ry here? Okay, that's a good question. It's because it merges easily with the problem. We know that the amplitude of the one state which we are interested is a good state is given by generally sine, right? Sine theta by 2. So theta by 2 is nothing but arc sine square root of the probability, correct? Or sine inverse of square root of p, correct? So which is nothing but square root of p. Sine arc sine square root of p is square root of p. That is what we are interested in. So that is why we are using RY gate. And amplitude of zero state is simple, right? Once we know this is square root of p, this should be a minus square root of 1 minus p. Or if you want to derive, you can start from cos square theta plus sin square theta equal to 1. From there you can get 1 minus p. Got it? Okay, so this is for a single borrower case, which practically, I mean, that will not happen. And for better understanding, I thought let's consider three borrowers case, okay? And each one having an independent default probabilities. That the first borrower most likely zero point 0.2 with the I mean, he will become a defaulter with a probability of 0.2. So like that 0.2, 0.4, 0.5. Now I want to do an analysis. Okay, what's the analysis? What's the objective? What's the probability of at least one borrower defaulting? Okay, so now how do I do that? So let's look at what are the possibilities. Okay, so there are 2 to the power of 3 possibilities, right? That is where I'm telling when you have multiple borrowers, 100 borrowers, 1000 borrowers, if you want to do thorough analysis, you need to do large amount of computations. Of course, practically you may not need all combinations, but in case you need for some, okay, for a stock, picking up the right stock, okay, you may have to do such a complex thing. So in that case, quantum computing becomes very useful. Okay, coming back to our problem. What's the probability of at least one borrower? So the total possibilities are for one person, at least one person defaulting, the first guy alone, second guy alone, third guy alone, or 1 and 2, 2 and 3, 1 and 3, or all three bad guys. Okay. Of course, there is another possibility that all are good guys, that none of them will default. Okay. So in order to do, it's instead of doing each one, you can take this one. This becomes no default case, and then once you get the value, subtract from 1. So that's what we are going to do. The probability of at least one borrower defaulting is 1 minus P no default. So we are going to calculate P no default. So how do we calculate? So this is probability of defaulting. So no default, 1 minus P1. Similarly, 1 minus P2, 1 minus P3. So we will end up with 0.24 for no default. But we are interested in at least one borrower defaulting, which is nothing but 1 minus 0.24, which is 0.76. Okay. This probability though appears high, but just one guy going bad, it's okay, it doesn't affect my bank. But my investor is asking me, what is the probability of at least two borrowers defaulting? Oh, okay, now I have to do my calculation all over again, right? So what are the conditions? Exact two, that is 1 and 2, 1 and 3, 2 and 3, and all three defaulters are going bad. So now I have to compute this step. How do I do that? 1 and 2, I know the probability. 3, no default, I have to subtract from 1, right? So 1 minus 0.5. So since it's 0.5, this is same as fault or no fault for the third guy. But for 1 and 3, 2 is not a defaulter. So we need to subtract 1 minus 0.4, 0.6. So you get a number like this. Similarly, for 2 and 3 default, we got 0.16. Now all the three becoming becoming defaulters, we need to just multiply the given three probabilities, which is nothing but 0.04. Now probability of at least two defaulters will get by adding all these four probabilities, which is nothing but 0.3. So, and suppose another problem is being defined. Okay, you need to recalculate, right? So in quantum computing, it can be done very easily. That's what we are going to see. All right. So let me go take the code. So this is the code. As I told you, I've taken from IBM community GitHub, but I made a major change. So there, the example given there was for one borrower, and I modified the code for three borrowers. All right. So our aim is to build operator A and Q. Operator A is easy to build, okay, by having, uh, okay, the probability is given as an input. Once you are given, then you take square root of P sine inverse, and that is the angle to be rotated, and that rotation should be with respect to y-axis. But operator Q is little tricky one, and that will vary the type of algorithm what we are going to use. So in order to differentiate, we are going to introduce another variable k that will take care of the different QAE algorithms, right? We saw 4, of course there are many more, okay? So, but ultimately this also will use ROI, okay? All right, and compared to this rotation, we may rotate twice what we saw in the slide. Now we are giving the inputs, probabilities of the three borrowers becoming default, 0.2, 0.4, 0.5, right? So the number of borrowers are 3, just taking from the number of probabilities entries. Now we are building the circuit by calling these two classes what we have built, okay? Now the circuit is built. These two are important steps. Objective qubits, which qubit we are interested in. For example, okay, in this case 3, so we are going to look into all the 3 qubits. Okay, each qubit represents one borrower. Understand? Because that you should be clear. if the problem size is more, we may not be interested in looking at all the defaulters, maybe specific, particular state or particular company. Okay, so that is where you have to assign which qubits you have to look for. And this is another important thing. So which, this is the problem one, right? Which one? Like I'm interested in at least one borrower, means at least one guy should, whoever is having a probability, I need to count. Okay, so the count, I need to put one here. Okay, is good state, is it good or not? Suppose if I want to say at least two borrowers, then I have to make it two. If it is for three, I have to put three. Now we are putting all together and calling it as the problem. So it's an estimation problem. So all these new functions, what you see, they're all given in the Qiskit algorithm libraries. Okay. So in the problem definition, what we are saying, calling the A circuit, Q circuit, which qubits we need to look for, and what is the good state for your problem. So that is what is defined. Afterwards, you call Qiskit sampler method. Then I told you there are many quantum QA algorithms. We are going to use iterative amplitude estimation. That's what I told you in that comparison of different QAs, right? That slide where we compare. So here you need to define two more parameters. What are they? So one is the target accuracy, which can be small as possible. If it is becoming too small, then it will take more iteration, right? So you will become an expert in choosing this number once you're done sufficient number of calculations. And alpha is the confidence level. So that again, the lower number may be a better one. But you have to consider the number of iterations. Once you call the function, then you estimate or execute with the problem defined, you get the answer. Very easy, right? So let's run it. I think we need to get somewhere around point 0.7, yeah, 0.76. So this is the probability of at least one defaulter in our three borrowers. Okay, now I want to get what's the probability of two guys becoming defaulters. Very easy, you see. I don't have to do big computation. 0.3. And I want to know all the three going bad. That is 0.04, right? All the three guys are going bad. Just run it. Wow. So now you will appreciate the quantum computing, right? The power of quantum computing. You are able to do multiple possibilities with very simple calculations. Okay. I also want to show you something how the circuit will look like. So this is particularly for one type of amplitude estimation function. I think they used something called amplitude estimation algorithm. So wherein when you collapse when you decompose the circuit, it will look like that. So this is where for even I mean there's a whole circuit is done for one borrower. You can see here 3 qubits plus 1 qubit. This is count. Okay, I hope you are aware of QFT, right? So if you have more number of qubits, you will have a better accuracy, and it's very complex. You have to do QFT also. Okay, and if this is at a first level, if you want to decompose at full decomposition, if you want to do, then you can see the number of gates are going high, and instead of Hadamard gate, they are using 3 U gates. Of course, only one is effective, the other 3 are like identity. There is no angle value, right? All are zeros. So I am trying to, okay, what I want to convey from here is, if you want to understand each and every gate, you can do that by decomposing the circuit, and later you can build something similar to that. But if you just want, your interest is more on finance, you just don't worry about the depth of the problem. We just call the desired or required method or function available in Qiskit. Okay, so I hope you understood. What I'm going to do in my next video, I'll try to cover the application of QAEs to different financial uh, problems or analysis, right? So possibly we may start with the options pricing. So in options pricing, what you'll do? We're interested in the expected value with from different assets. X represents different assets, and f of x is the payoff, and p is the corresponding probability. So our aim is to come out with the probability of getting an expected value of so and so for the given set of assets. For VAR, CVR, we encode the loss distribution, and QAE estimates the tail probabilities and conditional expectations. For portfolio optimization, our objective functions involve expected values. It may be a return or shortfall, and QA computes them more efficiently. We have already seen quantum optimization algorithms. Again, if you want to know more about that, see my videos. Derivative pricing. So it's something similar to options pricing only, but at a higher level. Okay, allows efficient estimation of expected payoffs under various simulated paths. It's much superior than Monte Carlo simulation. Credit risk analysis encodes credit scenarios and simulates rare but impactful events more efficiently. All right, so in my next video, I'll try to take a couple of examples and let's see how quantum computing is more useful compared to classical computing. So these are all some of the references. I think I told you earlier that IBM Qiskit community's GitHub gives a nice web page to cover the complete quantum amplitude estimation. And in fact, they also given references how they arrived at. Okay, so that will help you to modify the existing algorithms or come out with new algorithms. Okay. Thank you very much for seeing this video. I hope to see you soon with more videos. Bye bye.